Right. Okay. Thank you very much for your kind introduction. And first of all, I would like to thank JpGU and Nishida Sensei for this award and the opportunity to talk here about my research. And today I would like to present some recent advances in upper atmosphere and how it's related to space weather. In the following, I first gave a short introduction about the ionosphere-thermosphere system, often referred to as the upper atmosphere. And this is followed by some examples demonstrating how the ionosphere-thermosphere system is connected to the sun and the weather, which is the science behind space weather. I also briefly talk about space weather forecast before wrapping up with where we stand and where we go next. And since this is a general talk, I will focus mainly on phenomenon rather than process. So if you are interested in knowing more physical processes, please feel free to ask later. So first, where's the upper atmosphere? And some of you may say everywhere above the cloud. And that's not wrong, but not accurate. According to textbooks, the upper atmosphere refers to the region between 100 to about 1,000 kilometers. And it has three features. The first is high temperature. And it can be very hot, over 700 degrees in comparison to like 20 degrees on the ground. And the second feature is that it contains a mixture of neutral and ionized gas, thus forming a ionosphere-thermosphere system, or the IT system for short. A third characteristic is very low density. And as you can see, around 300 kilometers, the density is 11 orders lower than the ground. So what this means is that the upper atmosphere above 100 kilometers holds only 0.003% of the total air mass. So you might say, that's very thin, and who cares about it? And well, some don't care, it's so thin, but some do care. And those who want to live as a modern Homo sapiens. And they care because the ionosphere-thermosphere system has become an essential part of the infrastructure of the so-called Society 5. And why is that? As the gateway to space, the upper atmosphere hosts many rockets and also Earth-observing satellites. And through the satellite drag, the thermosphere affects the satellite orbit and also lifetime directly. And secondly, the charged particles in the ionosphere will affect the radio wave propagation and therefore affect the communication and navigation systems. So satellites, communication, navigation, and these are all the keywords of the infrastructure of our modern society. And for their smooth operation, it is important to know the structure of the IT system and how it changes with time. So let's first have a quick look at the global structure of the IT system. And the ionosphere has been intensively studied since the 1950s using many measurements techniques such as ionosound, radars, and all kinds of satellite-borne instruments. Therefore, by now we know its basic structure pretty well. And this figure shows the global distribution of the plasma density in local time versus latitude frame. And this structure is mainly determined by electromagnetic processes and giving rise to a famous structure called the EIA, or equatorial ionization anomaly, which is characterized by a minimum at the deep equator and then two bands of high density in each hemisphere. And in contrast to the rich database of the ionosphere, And the thermosphere has very few observations, mainly due to the technical difficulties to probe the very thin neutral atmosphere. And for a long time, we have thought the thermosphere has a very simple structure, like shown here, which is totally driven by neutral dynamics, forced by the solar heating and with a maximum at the subsolar point. But recently recognized that this is actually not the case. And the accelerometer on board the CHAMP and GRACE satellites in the past decades have provided us very high resolution measurements, which update our view on the thermosphere. And one of them is the magnetic control of the thermosphere, as shown in 3 features on this slide. The first is the equatorial mass density anomaly, as shown in the upper left figure. And opposite to the long-believed subsolar maximum, can see the density actually form a minimum, sandwiched by 2 density crests on both sides, and therefore similar to the equatorial anomaly in the ionosphere. And at high latitudes, we can see the density form some cells in response to the energy input from the magnetosphere via particle precipitations. And also in the global wind distribution in the lower left figure, we see the strongest wind is found to follow the black line, which is the geomagnetic equator. And all these features demonstrate the strong magnetic regulation of the neutral atmosphere through the so-called plasma-neutral interaction. So now let's have a look at how the IT system changed with time, which is related to the space weather, we say. Recall that the upper atmosphere has a very low density. Thus, it is highly dynamic and responsive to external energy input from the sun and the weather. And such energy input can produce IT disturbances at various time and spatial scales. And such disturbances have been called space weather since the 1990s to reflect its practical impact on our daily life. So you can see that basically IT disturbance and space weather are the 2 sides of the same coin, with the IT disturbance being the scientific side and the space weather being the practical side or application side. In the following, we will have a look at some examples about the space weather driven both by the sun and also the meteorological weather. So first, let's have a look at the space weather driven by the sun. The solar-driven space weather has been very well known, and we know when there is the flares and coronal mass ejections occurred on the sun, and when they reach Earth, they can cause a huge disturbance of the Earth environment, which are collectively called magnetic storms. And the effects of magnetic storms are multifaceted, including the beautiful aurora, but also not so beautiful effects like radiation, charging, and power outage. At the same time, it can also affect the neutral atmosphere, as shown here. So on the right side of this slide, this figure shows the temporal variation of the thermosphere density in the famous Halloween storm in October 2003. You can see that in response to the storm, and the density has a very quick response in the polar region and then propagate through the whole globe within a couple of hours, leading to enhancement of the thermosphere density by 6 to 10 times. And this effect is called the thermosphere storm, which has a significant effect on satellite operation through the effect on the satellite drag. And this would cause a serious problem for satellite tracking and therefore increase the danger of collisions and decrease the lifetime of satellites. So very often satellites are lost tracking after storms. The most famous one is the 1989 one, and caused more than 1,000 objects to lose tracking. And in contrast to the very remarkable space weather effect driven by the sun, and the IT disturbances driven by the weather from below are relatively mild and therefore only recently been discovered. So in the following, I will show 3 examples to demonstrate this coupling at different time and spatial scales. So they are the land sea topography and earthquake tsunami and the stratosphere sudden warming. Now first, let's have a look how the land sea topography project its impact into space. And the interchanging land sea distribution in tropical regions is a feature that is unique to Earth and is essential to the habitable climate we live in. And this surface topography causes the cloud to have a similar longitudinal variation as shown here. Is not, and the but what is interesting here is that its influence does not stop there, but further extends above the cloud to the space. And these upper figures show the global distribution of the thermosphere and ionosphere density. The 2 bands you see are the equatorial anomaly we mentioned in previous slides. But the point here is the structure in the east-west direction as indicated by these 4 white dashed lines. And they show a 4-peak structure which is very similar to the longitudinal variation of the cloud, and therefore showing a connection between the space and the ground. So how does this teleconnection happen? And a long story made short is that the deep convection in these clouds and can generate a type of atmospheric waves called non-migrating tides. And these tides, they can easily propagate to the upper atmosphere and therefore modulate the thermosphere and the ionosphere. So the connecting agent here is the non-migrating tides. Now, at the local scales, the meteorology forcing can also cause very dynamic changes in the ionosphere. And for instance, what you see here, this movie, is the ionosphere being shaken by the Tohoku earthquake. And before the earthquake, let's go back a little bit. So this, what you see is the ionosphere TC map on the Tohoku earthquake day. And before the earthquake, you see there is almost no structure in the ionosphere. But once after the earthquake, and there is very dramatic structures shown there, which we have never observed before. And now let me play it one more time so that you can watch clearly. So now, and I remind you that what you are seeing is not the sea surface. So this is 300 kilometers above the sea surface in the ionosphere. And So in this movie, we recognize that there was very rapid response in the ionosphere about 7 minutes after the tsunami was launched, with concentric waves which has lasted more than 3 hours. And some simulation work have shown that the connection in this coupling is mainly performed by the gravity waves and also acoustic waves, which are launched by the earthquake and tsunamis. And here is a third example. And different from the previous 2 examples, where the forcing or the source of the forcing are all sitting on the sea surface. And this third example, the source is sitting above the cloud in the stratosphere, as the name indicates. So stratosphere sudden warming is an event occurring in the polar winter, where the temperature of the density suddenly jumps over several tens of degrees within a week with the polar vortex distortion. And recent studies have shown that this very local event in the stratosphere has a global impact on the upper atmosphere by modulating another type of atmosphere waves called semidiurnal tides, which also propagate up to the upper atmosphere. As you can see here, it can cause the thermosphere cooling, which shows very clearly about 40-degree cooling during the middle of the stratosphere warming. And also in the ionosphere, it shows a enhancement of the TEC in the morning sector and a depletion in the afternoon sector, and therefore showing a feature of semidiurnal tides. And there are many other examples which I do not have time to show here, like solar flares, global warming, and they all show the coupling between the sun and also the ionosphere and also the lower weather, meteorological weather. And through all these examples, I hope by now you have a large picture about the Sun-Earth connection, which has 2 characteristics. The first one is this coupling or this connection is involved both plasma and neutral, and at various time and also spatial scales. And a second characteristic is this coupling is in 2 directions, including the downward coupling from the sun and also the upward coupling from the ground. And currently, our understanding of the upward coupling is very poor. And although we know that the coupling is mainly carried out or performed by the various type of atmosphere waves, like tides, gravity waves, and planetary waves, we do not know how exactly these waves are propagating up and how they interact with the background ionosphere and thermosphere. And the main reason for this is a lack of observation in the MOT region. Now let's turn to the other side of the coin, the space weather. Now the space weather effects affect the infrastructure of our high-tech society. So it is highly desirable to forecast these impacts. And by now, space weather forecast has become a major goal for both science organizations and also government agencies. So same as the normal weather forecast, and a space weather forecast can only be useful. It can tell us when and where a storm would happen and how big it will be and how long it will last. And for this, for when, and I think space weather forecasts need to tell us forecast arrival time by observing not only the sun but also the solar wind in the interplanetary space. for accurate estimation of the arrival time. And as to where, the forecast need to increase its regional capability by taking the mesoscale and small-scale features in the IT system. And as to how big and how long, we need to take into account not only the solar forcing we have been so far doing, but also the impact of the meteorological forcing from below by enhancing our understanding of the coupling process in the MLT regions. And currently, for the prediction purpose, the empirical models and also the machine learning are also being applied to this quarter of the space weather research. And so to summarize, and the ionosphere-thermosphere system has become part of the infrastructure of the Society 5. And because it's driven both by the sun from above and also the weather from below, we need to take a whole atmosphere concept to take into account the plasma neutral coupling at various scales in both time and space. And for the next generation advancement, I think the interaction between the upward and the downward coupling, and also to fill up the MLT region observation gap, and to develop also non-hydrostatic models, which include meso and small scale features, would be very important. So in short, for the next frontier space weather science, and I think it lies in how we can connect the space physics and the meteorology. And towards this direction, and I think the current satellite constellations, including the Icon and Gold from NASA, and also the Swarm satellites from ESA, and they will provide us a good opportunity to make breakthrough towards this direction. Finally, taking this opportunity, I would also like to thank my mentors here, and without whom I wouldn't be here actually, and Professor Yamamoto and Professor Watanabe and Dr. Richmond and Professor Liu for recommending me to this award, and also for their continuous and strong support throughout of my career. So with that, I thank you for your attention.